Using what we learned in the previous video, that we can solve for even and odd solutions for this finite square well potential for bound states, we will launch into that and look first of all at the even case. So I'm going to be looking for the even solutions to the one-dimensional time-independent Schrodinger equation, where of course, since the potential is symmetric, then I know that I can look for just the solutions to this equation that are even functions of x. And then we'll look individually a little later at the case where we're looking for odd solutions, and then ultimately you can combine those two back again to get the most general case where you have both the even and the odd pieces. Well, there's our function, or our potential energy well. We're looking for bound states, and for bound states in this, when the potential, it's an attractive potential that vanishes at plus and minus infinity, then then for bound states, the energy of the particle E is always negative. So it's a negative value. So I've got a particle that's trapped in here, and I'll draw this horizontal line to indicate its energy. I've got the depth of the potential is given by V naught. V naught's a positive number that I assume that we're given or that we know. And it's the deeper the well is, the larger V naught gets. It gets more and more negative. We'll write this in several different ways. Sometimes it's convenient to think of it one way as opposed to the other. But if you look at this, the energy E is between 0 and minus V naught all the time for these bound states. Another way to say the same thing is if I take the absolute value of the energy, it's got to be less than the depth of that well V naught. And if I plug the fact that E is negative, well, it's obviously, I could write this E as minus the absolute value of that E. And sometimes we'll write it in that form as well. And now we'll just look to get solutions on the positive side, because I know that if it's an even solution psi of x, once I've got that, then I can just extend it symmetrically to the other side for the negative values of x. So let's do that. So first, just look in this region when x is between 0 and a. And our equation now becomes, in that region, the potential of x, v of x, is just minus v naught. It's a constant all the way here. And I have this equation to solve. First thing I'll do is bring this over to the right-hand side, and you'll get v naught plus e. And since e is negative and v naught is how deep it is, V naught being positive, well, this number here is always going to be a positive number. V naught essentially minus the absolute value of E, but the absolute value of E is less than V naught. So this quantity in parentheses is a positive number, and if I really emphasize it, I could write it like this. And I'll solve that for the second derivative, so multiply through by 2m, multiply through by the minus sign, and then finally divide by the h bar squared. And now then this term, I'll get a minus, and then this whole term here is going to be positive. And I can then write that, identify that fact, and I'll just let k squared be that positive term, the 2m v naught minus the absolute value of the h bar over h bar squared. And then most of the time I'm going to write it like this, and just realize that the energy is minus its absolute value here, so that this is a negative value. E is negative. It's constant, but it's negative. With that, our differential equation up here becomes psi double prime is equal to minus k squared psi. Get that in the standard form. And as we've seen before, we can write that in one of two forms, either sines and cosines or e to the ikx, e to the minus ikx. In this case, it's easier to do the sine cosine, keep everything real. And our most general solution is an arbitrary constant times cosine kx plus another arbitrary constant times sine kx that solves this equation. However, now we invoke the fact that we're looking only for even solutions. And cosine is an even function, but sine is an odd function, and so that forces us to choose b equals 0 if we're only looking at even solutions. So for x between 0 and a, I get a cosine kx. Do a similar thing for x greater than a. That's really even easier in a certain sense, because for x greater than a here on the outside, then this is the potential 0. I'm in this region up here. So our Schrodinger equation in this case simply puts a 0 here, so it vanishes. I've got this term, the potential term is 0, 0 times the wave function psi. And I can again just note, I suppose, that I can write this energy. The energy is negative, and so I could write it as minus its absolute value. And then I have the two minus signs and come back to this. So that explicitly shows that this constant that's in front of psi is a positive constant. But again, I'm going to take to writing it like this. If E is negative, then to make this all positive, I have minus 2m E over h bar squared. So alpha squared is this or this. Most of the time we'll write it like that. And our equation now, once I've defined this alpha squared, is given here. And moving back over to the left-hand side, we get the general standard form. And again, that's one that we've encountered before. And the general solution is c e to the minus alpha x plus d e to the alpha x, where alpha squared is this value here. Again, this is a positive constant since e is negative. Well, this is going to be good for the entire region x greater than a, and that includes x equal to infinity. And so this solution must remain finite, and in fact go to 0 as x goes to infinity. This term is okay. E to the minus alpha infinity goes to 0, but this term blows up, and so to be able to have normalizable solutions, x has to go to 0 as you go to infinity. And so to accomplish that, we have to choose d identically equal to 0. Otherwise, we don't have a normalizable solution. And then we've got the solution. Most of the time, I'll write it like this. And that this is pretty standard, although it's not the easiest thing to interpret, probably. But from x between 0 and a, it's this cosine function. For x greater than a, and then for x less than a, I just use the symmetry, the fact that it's a symmetric function, that psi is an even function. I'll spell that out in a little more detail here in a second. So when x is between minus a and 0, I simply let x go to minus x in the corresponding part on the other side from 0 to a. So let there it's a cosine kx, so let x go to minus x here. But since cosine is an even function, the cosine of a negative argument is the same as the cosine of a positive argument. So that goes through. The other one is a little bit different because now I look at c e to the minus alpha x. This is for x greater than 0. So for x less than minus a, I'm sorry, for x greater than a, for x less than minus a, I simply let x go to minus x in the x greater than a solution. And when I do that, this c e to the minus alpha x, let x go to minus x, it becomes plus alpha x. And to write that out in full, which I almost never will probably, most authors don't, we have our solution on the positive side, 0, x between 0 and a, and x greater than 0, that's the one we originally solved for. But now that we've extended this so that it's an even function, this psi even, psi of x is even. And so from minus a to 0, it's the same function. And then for x less than minus a, it becomes e to the alpha x. And you'll notice as x goes to infinity, this term vanishes. As x goes to minus infinity, this term will vanish. To kind of illustrate the process, we're going to get wave functions that look more or less like a couple of these things that I'll draw here. Let's suppose that I've got in this side just one hump and a cosine function. So this is a cosine. It's a cosine on both sides. It's the same cosine function. So from minus a to a, it's just a cosine function. And we need to match it up to these exponentials at the x equal to minus a and plus a. We'll do that in the next video, in fact, and see what conditions that occurs. So there's the very first wave function that will look like that. I can go really any kind of a cosine function in between with more wiggles in it. Here's the next one. I get a function that's a cosine function in here, cosine function here. Again, it has to go exponential decay out here, and e to alpha x as x is negative, it goes down here, and we'll have to match them up. Now, we really have only found the solution f of x on this side, which is the combination of these two. And then to get the wave function on the other side, I just take whatever the positive function is to make it symmetric and make the wave function on this side be equal to f of minus x. So everything that's over here, I put a minus x in, and then generate the solution. So we'll get a whole series of wave functions that will match up something like this. And I've drawn really the first two of these. Like we've done before, the more wiggles it has in it, the more turns it has, the higher the energy is. So this is really the lowest energy state. So this is a ground state, this one here. This one would be the first even higher energy solution. And I think that's it on this one. Yeah. Well, we'll pick up here next time and do the matching at these two boundaries and see what that leads to.